those that don't know, Malta is a small island off the southern coast of Italy, and that's where we did a lot of our research this summer. We worked with the University of Malta, because Malta is significant because it was a major port during Greek and Phoenician trade times. And as we know, where there are ships, there are bound to be shipwrecks. So we wanted to focus our work on the shipwrecks there in Malta. So currently, the marine archaeologists at the University of Malta have to go down and dive these wrecks, which you can see a little bit of that here. Yeah, so they're highly skilled technical divers that go down and do this. The problems with this is that it's incredibly expensive. The equipment is expensive. Getting the boat out there, getting the divers out there is expensive. It's also incredibly dangerous. Like I said, these are highly skilled technical divers, but even still, the danger is there. They have limited depth. People can only withstand so much pressure. You can only go down so deep. And then with that, there's also limited time. If you go down to a certain depth, you can only withstand a certain pressure for so long. So if you're at 100 meters, you can only stay on for about 20 minutes, which severely limits the data that you can collect off those wrecks. So our goal was to aid these marine archaeologists by detecting and mapping wrecks using autonomous underwater vehicles, or AUVs. So here was our primary process. So we start by detecting wrecks using image processing algorithms, and then from those wreck identifications, we can create a preliminary mission, and then we can run our path planning algorithm to determine how we can further explore the wrecks. And then we can run that mapping mission, and from the camera data that we collect during that mission, we're able to create 3D visualizations of the wrecks, which we can in turn give to the archaeologists at the University of Malta for further study. And then Zaira's going to talk a little bit about that wreck detection process.
Right, so before we actually collect any data about these shipwrecks, first we have to find them. And we do this through wreck detection. And the primary device that we use for that is side-scan sonar. So side-scan sonar is a device attached to the bottom of the AUV, as you can see in this picture, and it kind of scans the ocean floor in a conical shape. And the reason that we're using that for wreck detection as opposed to a camera is that it has a deeper range than like a camera would visually. And so we can use this for detecting shipwreck locations. So on the next slide, we have an example of a side-scan sonar image. This black line running through the center of the image is the shadow of the AUV. It's scanning on both sides of the AUV. Can anyone spot the shipwreck in this image? It's a little darker, but maybe. Well, it's right there. These days, what marine archaeologists have to do is actually scroll through thousands of kilometers of ocean floor data, just like this, in order to spot potential images of shipwrecks. So this is a zoomed-in image of the shipwreck we saw in the previous slide. And so we're going to try to automate this process because clearly it's not very efficient to scroll through all the data and look visually to try and identify shipwrecks. So we're using some image processing techniques in order to speed up that process. Our first algorithm for detecting shipwrecks is line detection. And the reason we're using this is because in a lot of manufactured objects, you have more linear patterns than in natural found objects. So where there's a high density of linear regions, we can circle that whole area and identify it as a potential shipwreck. The second method that we're using for shipwreck detection is peak detection. So this is just looking for bumps on the ocean floor by searching for dark spots followed by light spots. As you can see, this whole edge there of the shipwreck has been identified as areas where there's a shadow, or like the beginning of a shadow. And so that whole area can be identified as a potential wreck as well. And the third method that we have right now is gradient detection, which does something similar, but instead of just looking at dark spots followed by light spots, it looks at the change in pixel intensity around like a whole area, to the left and right, up and down, and then identifies those regions as potential, and they identified that whole region where there are lots of clusters of gradient change as a potential shipwreck. All right, so now that we've identified where there could be shipwrecks in the ocean floor, Vlad's going to talk about how we get to those shipwrecks and what we do over there.
So as Zaira said, we use image processing algorithms on the side-scan sonar data to detect shipwrecks. And using that data, we can then do a preliminary mission and then plan paths to create reconstructions of our shipwrecks. So the goal of the path planning algorithm is to plan paths around a given shipwreck so that we can optimize the camera viewing angles, because with these optimal view angles, we can create much better 3D reconstructions using camera footage. So first, we need to find an area of interest. These are the areas with the shipwrecks in them. Here's an example of some sonar data that we collected. As you can see, there's a slight shipwreck. It's kind of hard to see. It's a plane wreck, actually. And we can use different algorithms to identify areas as areas of interest. One of these algorithms is gradient detection. And using gradient detection has this effect. So as you can see, the area with the plane wreck actually pops out significantly. So these areas can be given a much higher score. And so the yellow areas have a high score, and the blue areas have a low score. So what we want to do is maximize the score, so seeing more of the bright yellow areas. So the path planning algorithm that we use is known as a rapidly exploring random tree, which is a generally well-studied algorithm in literature, but we did have some extra modifications for our application. The way this algorithm works, as you can see in the graphic, is it just has the start location of the AUV and then randomly chooses directions to expand. It also uses the dynamic constraints of an AUV. The AUVs can't move sideways, they have to move only forward and turning. And then it just keeps branching out, and after a certain period of number of trials, it then calculates the score of the different paths and chooses the path with the best score. So with this algorithm, we implemented that, and then we also implemented a couple modifications to the algorithm. The first modification is, instead of just randomly choosing a direction to expand, we tend to expand in directions with higher scores, so we know that we're getting closer. So we can get to the goal that we want without having to do as many iterations of the algorithm. And the second step is actually pruning nodes without a very high score, because it's not very likely that there's a good score in that direction. We want to remove these extra nodes. So here's an example of the original implementation of the RRT algorithm. The little blue lines are just the randomly generated paths, and the chosen path with the best score is the red line. As you can see, kind of loops in a few circles and eventually gets down to the shipwreck. So with our modifications, we have the following result. As you can see, it goes more directly toward the shipwreck and is much faster. Here are the general results. So with the number of trials that you have, the better the score is. So that's the x-axis is the number of trials, and the y-axis is this path score on average. So the blue line at the bottom shows just the general RRT algorithm. The green line shows how the algorithm performs in pruning, and then the red line shows how the algorithm performs with high information configurations or the expansions in directions with high scores. So then these algorithms were put onto a robot, and they were deployed over shipwrecks off the coast of Malta. We spent a month over the summer deploying these AUVs over shipwrecks. It's kind of hard to see because it's a little bit dark. There's a shipwreck. Yeah. Cool, so now that I've talked about the path planning, Zaira is going to talk about the visualization component of the project.
Right, so now we've collected a bunch of video and sonar data of the shipwrecks. So in order to put this into a form that archaeologists can better study, we created 3D reconstructions of the shipwrecks. So this is another example of the AUV going over that same wreck you saw in the previous video, but a little more clear here. You can see all the jellyfish flying by. There's the shipwreck there. So we collaborated with 3 students from Cal Poly San Luis Obispo who were in Malta with us this summer, and they were the ones who took the video and sonar data and created reconstructions using that data. So here's an example of a 3D reconstruction created from the sonar and video data collected of this shipwreck. This is in Manimal Island in Malta. It's an 8 to 10 meter deep wreck. The next video is a plane wreck. It's significantly deeper, over 30 meters deep, off the coast of Malta. This is a Bristol boat fighter from World War II, and this is actually a camera on the AUV as it flies by the wreck. And then this is a 3D reconstruction generated by Cal Poly students of this plane wreck. They use Agisoft PhotoScan to generate these reconstructions.
So in summary, we talked a little bit about the wreck detection process, the 3 image processing algorithms that we were able to implement, and then I discussed our path planning algorithm to gain a little bit more information, some camera data from the wrecks that we detected. And then Zaira also talked about the 3D visualization going on with our group that we collaborated with at Cal Poly San Luis Obispo to create those 3D visualizations that you saw. That was so cool. So in terms of our future work, we're hoping to incorporate another image processing algorithm that looks at texture analysis, so looking for like bumpier areas and things like that that may indicate a shipwreck could be there. We're also hoping to use real-time detection and path planning, so an onboard process. Currently we're doing it all offline and loading it onto the robot, so it'd be nice to have it all going on board. And then we'd also like the opportunity to look at deeper wrecks. So we're limited by the equipment that we're using, but we'd love the opportunity to explore more wrecks by being able to go to a greater depth. And then we just want to acknowledge Dr. Timmy Gambine, the archaeologist